All right. Hello, everyone. Um, Hope everyone's having a wonderful afternoon. I moved the stream a little bit earlier than usual, but I figured it would be best to have more time to work on this project, especially because I mean, we're probably not going to get this done in time for the holidays. But best to try. Oh, hold on, I'm not even on screen. Hello. All right. So yeah, if you weren't here last stream, we are making a hardware USB soundboard. So it'll be a physical electronic device that you plug into your computer through a USB port, and it shows up. Basically, it'll show up as like a microphone, but then it has physical buttons, and when you press the buttons, it will play sound through that microphone. So last time, we kind of settled on the part number we're using as our main microcontroller. It's a 32-bit ARM processor. Specifically, the ST Microelectronics STM32H723VET6, which I should grab that data sheet. Let's see. I really should have just saved it so I don't have to go find it again, but there we go. So yes, this is a ARM Cortex-M7. Probably a little bit more powerful than what we need. But I am happy to have that extra wiggle room in terms of power, certainly, especially for our first prototype. As I mentioned last time, I've never really worked with USB devices before, so this is fairly new to me. Also, if you weren't here on Thursday, you might notice that I sound a little bit different. I just upgraded my GPU. I have an RTX 3060 now, which means I can use NVIDIA's noise cancellation technology, which I feel like, from the test we did on the stream on Thursday, I feel like it works better than the other options available in OBS. Which is good, because my main goal is to, suppress noise, but also not suppress any of me talking, which I feel like the other noise suppression algorithms either don't suppress the noise very well at all, or suppress a lot of me talking and laughing and such. Yes, a 32-bit ARM Cortex-M7 with some hardware acceleration for floating point operations, and this one specifically had an interesting little feature where it had accelerations for calculating filters. So that being ways of distorting audio, essentially. So it has a hardware accelerator for that. That being said, of course, the microcontroller is the central part of the design. It's very important, but it is far from the only thing we need to worry about. So let's get right into it. All right. So like last time, I am just going to go ahead and put on something to listen to while we are doing this work, so it's not just me talking over a blank void. Let's see. So the moods we have available are 1337, amped, chill, footwork, good vibes, and popped. Now we went with chill last time. If someone in chat wants to make a suggestion, I would be happy to change it, but otherwise I think I am just going to go back to chill. Oh, and do you know what I need to do? I need to make it so that I can actually hear the darn thing. Give me just one moment. Switch that over. There we go. Lovely. See how those levels are. A bit quiet. We're so far from the ground, but I'm not looking down. Oh, I really wish there was a switch that would let me, like, turn off tracks with vocals in them. Now we're soaring high. This is a bit much for background. Okay, so yeah. So I was thinking about the possibility that instead of just like a micro USB connector, we could put in a USB-C just for, you know, future-proofing. Really, both standards are going to be around for a while, of course, but USB-C, especially like learning how that works now, would probably be nice to be able to do, because that's what things are kind of moving towards going forward. So yeah, that being said, so USB-C, the connector, is different from like the high-speed data protocol. And oh, wait, I'm using a slightly out-of-date version of my model. So I made a... I'm working on some big upgrades, but in the meantime, I made a slight change. There we go. Okay. So with that fixed. So yeah, the USB-C connector, which is this thing, the one that you can plug in either way, is different from like the high-speed data transmission and the like power delivery protocols. So those run over that connector, of course. But you don't have to use those advanced protocols. You can just use a good old like USB 2 connection. Which is good, because that's what we have the Phi for on this thing. Yeah, we can use the sort of physical layer here, which is the thing that actually handles the signaling and the sort of weird analog differential stuff, while using a USB-C connector, but we have to do some sort of bridge logic, basically. As if you'll notice, this connector has a lot more pins than your average, you know, USB-A connector with its classic power ground D+, D-. This one, if you'll notice, so it's designed, and you can probably see just looking at it, it's designed to be able to be plugged in both ways around and be fine either way. So if you just flip this around in your head, you'll notice that when it's one way up, there's this TX plus pin here, there's this TX plus pin would be if it was flipped around the other way. And basically, that adds a little bit of extra complexity, because we're going to be using, I believe, just the D+ and D- pins. But there's two sets of D+ and D- pins, and both of these are going to be broken out on our connector. Now, I think you can probably already see the potential issues with this. Actually, I think I'm ducking the background music a little bit too harshly. Let me turn that down a little bit. Testing, 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 testing. Yeah, that should be better. A little bit less. I don't want it to sound too awful when I start talking. Okay, so yeah, that means that we're gonna have two pairs of pins. Like D+ and D-. And only one of them is going to be like our active connection to the host computer. And the other pair is just not going to be connected to anything, basically. But the complicated part is we won't know until someone plugs in a cable which one is connected and which one isn't. And it could be either one of them based on which way the user plugs it in. So basically, we need to be able to communicate along either of those D+ and D- pins. Only one of them is going to be active at a time. You're never going to see both of them. But we need to figure out which one, basically. I was looking at some application notes here, and application notes are just like documents a company puts out to be like, here's how you use this product, basically. And they're a very handy source of engineering knowledge in this field. So if you take a look at this one, this is put out by Texas Instruments. Texas Instruments, I actually interned there once over summer of like 2020. It was neat. Yes, this is basically a application note, a 14-page document about various connection applications of USB-C. So what we want to do is this basic one. We don't need USB 3 at all, because we're just not sending that much data. We just need the audio connection. There extremely are specific documents. Hello, Audrey. Welcome to the stream. So yeah, the idea is, so this USB PHY, that's the physical layer that our microcontroller handles. This is internal to our microcontroller. This is the connector, and then we need sort of two additional things that we wouldn't need if we weren't using a USB-C connector. That is this USB 2.0 MUX, which is basically a chunk of logic that can tell, that controls whether to send the signal to these two pins or these two pins, basically. And this CC logic. Hey, listen, Audrey, I am always happy to answer questions. I know that this is pretty complicated stuff, and I'm trying to sort of explain stuff in a way that makes sense, but if you're ever confused about anything, please feel free to ask questions. I am always happy to answer them. And then this CC logic block. So this is a special feature of USB-C that basically, it's used for a couple of things. So on our end, all we need to see are these two resistors. These are the only part that we really need to worry about with this CC logic, except for measuring the voltage at this point. So, CC logic, the configuration channel logic block, it helps you detect the orientation of the cable. So, basically, there's going to be two sort of, two lines, so I believe I can show you them here. So this is CC1, this is CC2. These are both coming into our microcontroller, or coming into our circuit. One of them will be pulled down, which means it will be at sort of ground voltage. So the other side, the host, will pull this to ground voltage. The other, the one that doesn't get pulled to ground voltage is just left floating. And that helps us, by checking which one of these pins is grounded and which one is floating, we can tell what orientation this connector has been plugged in. And that's what we want to set our USB MUX here too. Right, and then it also just lets you detect the cable, right? Because if neither of these are pulled down to ground, then there's nothing plugged in. Not really much of an issue for our application, because frankly, if neither of these lines is pulled down, then we don't have power, so we don't need to worry about anything along those lines. And then this also tells us how much current we can draw through this device. So basically, this is a diagram of what it looks like. Like what the CC logic looks like on the source, which is like the host computer we're connected to, and then on our side. So we only see this side of it, basically. One of the lines is connected through, and then the other is either left floating or connected to ground with a high resistance. So essentially floating. So the way that the current detection happens, we put a constant resistance on RD, and I believe, let me see, it's in this application note here. They mention it is specifically 5.1 kilo ohms. So we need a 5.1 kilo ohm resistor. Ah, welcome back, Ghost Ninja. Yeah, nice to see you again. We are just going over some USB-C things, because I was thinking instead of using a like micro USB connector, like a standard one, we could just use a USB-C connector instead, just for forward compatibility. So I was just going over what we would need to do to make that happen. So we could use the same sort of physical layer. We can send just USB 2.0, which is just the standard USB, over the USB-C cable, sort of on its own without needing to implement any of the high-speed or power delivery stuff. But there is a little bit of complicating stuff. Yeah, it's a neat standard. So because the cable can be plugged in either way, that sort of adds more complexity to our side. It makes things easier for the end user, but it makes things a little bit more complex for us. Because basically, we're going to be using... When the cable gets plugged in, one of these D+, D- pairs is going to have a connection to the host, and we're going to send data through. The other is just floating. So, like, it's important... We need to, like, figure out which one of these D+, D- pins is actually the connection to the host every time the cable's plugged in. And then B, we need to actually, like, send our connection to the right pair. Now, for the speed of USB we're using... So this mux here, basically it takes our D+, D- pair from our, like, USB-capable microcontroller, and it splits it into these two, and lets us select one to use. And then the way we figure out which one is active is through this CC logic, the configuration channel logic block, which is two signals, CC1 and CC2 on the USB-C connector. And then one of them... Oh, hello, welcome to the stream, Continuous. One of them is connected through to the host. And one of them is either left floating or in some types of cable, that line will be pulled down, but presumably with a fairly high resistance. Oh, thank you for the follow! Yeah, I'm doing pretty well. How about you? So, yeah, that's how we can detect the orientation of the cable, is one of these will be pulled down on the other end, one won't. Well, hey, feel free to hang out here for a while. And yes, so this little configuration channel logic block also lets us decide how much current we can draw through the USB-C connector. I'm not quite sure how useful that'll be to us specifically, because I know Pancake has a... Pancake's computer doesn't have USB-C connectors natively, and even then we'd probably need to be able to handle the only getting the 500 milliamps anyway. Like USB-C, like actual USB-C hosts can supply even up to 3 amps without doing any of the complicated power delivery negotiation. But you can always just someone can always just connect to your device. This is an application note from Texas Instruments on USB-C applications. Yeah, if you want to look that up, it is... I believe I have a link to it. It's application note SLYY109 from Texas Instruments. I can link to it in chat. There you go. So what was I saying? Oh yeah, someone could always just use like one of those USB-A to USB-C connectors and plug in through that. And that's only going to give you the 500 milliamps that you would get over a normal, like, non-USB-C connector. So we could theoretically be able to use that, but we would need to be able to operate our device off of just 500 milliamps. Yeah, that's totally understandable. Feel free to ask questions. I'm always happy to explain stuff. I'm trying to, just generally explain my thought process and how the design goes, without getting too into the details. But please do ask questions. I am happy to explain things further. But yes, the way we tell how much current, the wire can have is, you can see there's this resistor RP on this side. I'm glad. Yeah, it's always important to learn. And we have a resistor that we have to implement on our side, RD. I've heard that some people just don't implement this resistor, which is very bad to do. That might come up. It's truly impossible to say at this stage of the design project. Let's see. So, yeah, these resistors basically, if I put this RD here, that tells the upstream USB-C device what's going on. So if I don't have anything here, if this is just grounded, the upstream device doesn't understand what's happening, basically. So if you've ever had like a USB-C device that only charges if you plug it in with a USB A to C cable, and like it won't charge if you plug it into an actual USB-C port, that's why they didn't put these resistors in here. And so the USB-C device that actually checks this just doesn't understand what's happening, and so it doesn't send your device any power. I always go all out with my resistors when I do little tests with my transistors because buying them is a pain. That's extremely reasonable. Yeah, I read an article on Hackaday that talked about that. It's apparently a very common thing that people do when they put when they're like manufacturing cheap electronics, is just not putting these resistors in. Which is silly because these are like this other application note has the specific values. But like they are, let's see, so to detect power, to detect the power level, you need a 5.1 kilo ohm resistor plus or minus 10%. Which we can check, on DigiKey, and it's probably just going to be like, I don't know, half a cent. Let's see, these are extremely accurate, like 0.25 resistors. We don't need to do that. Let me... I might just be confused by what I've put in the tolerance in the text box. But yeah, like, if you're buying these in bulk, even, like, fairly accurate ones are gonna be cents on the dollar. Yeah, sometimes it doesn't work too well when you do it with the search bar. So let's check real quick. Plus or minus 10%. Resistance, 5.1 milliohms. Let's select that or like to 1%. And then we're in the milliohms here. It's annoying that you can't just like search this because I do need exactly 5.1 kiloohms. Let's see, 900 results. And yeah, this 5%, 5.1 kiloohm resistor would do just fine, and in bulk, those are 0.2 cents each. So apparently a lot of cheap electronics manufacturers have made their devices totally incompatible with actually plugging them into other USB-C hosts, just to save 0.2 cents per device. Okay, that said, so basically these pull-down resistors, do I like math? I mean, I'm an engineer, so I like math fairly well, but I wouldn't say I'm, like, in love with it, you know? I'm ambivalent towards math. It is a useful tool, but, I don't exactly do calculus in my spare time. Okay, so yes. So if we look at this diagram, the combination of this RP and RD here, basically that makes what's called a resistor ladder. And you can tell, so if you know, let me figure out the best way to explain this. So if you know the value of RD, competitive math, I used to. In, like, high school, I did mu alpha theta, but I don't do that anymore. Yes, so the combination of these two resistors, if you know RD, you can measure the voltage here in the middle and tell what the value of RP is. Which is just, like, a neat little, like, electrical engineering, you know, like EE 101 thing that is used fairly commonly, but you know. So in this case, that is how we tell how much current we can source. It gets encoded in, like, the analog signal of this voltage. So because our RD has to be 5.1 kiloohms. Yeah. So because our RD has to be 5.1 kiloohms, the person manufacturing, like, the USB hub or whatever port this is connected to can the port this is connected to can set RP to create a specific voltage here. So that's how the device tells us how much voltage or how much current we can draw by this voltage value. So we will need to use one of our microcontrollers, ADCs, analog to digital converters, to measure the voltage at this point and compare that with the table somewhere around here. Right here. So this table right here, can't describe how happy I am to find someone also interested in competitive math. Yeah, like I said, I don't really do it anymore, but I definitely did in high school. I went to a high school in the same city. So in my city, the city I grew up in, there were two high schools. There was the high school whose math team always, like, came first in nationals. like national Mu Alpha Theta competitions, and then there was our high school. So we never really had that much of a chance because we were the other high school in the city with the high school that always like won nationals. So, it was a pretty laid back math team environment, which I certainly appreciated. Let's see. Yeah, basically we can check this pin voltage and that tells us how much current we can draw. So if it's 0 to 0.25 volts, have I tried IMO? Not sure what that stands for. That means there's no connection. So basically, you know how some of these have a ground connection through this? If it's less than 0.25 volts on the wire, then there's no connection. If there's... So sorry, I think I might have said it was grounded on the other side, when the one that's connected. It is not grounded. It's held to a positive voltage. And then... if it's between 0.25 and 0.7 volts, that means it's like a USB A to C cable, basically. Like someone's built a USB A to C cable and they've connected it to a USB A connector that can only source 500 milliamps. Which, by the way, apparently early on people weren't making their cables very well, so they would, like, International Math Olympiad. No, I never did that. No, our math team did Mu Alpha Theta. So yeah, if it's between 0.25 and 0.7 volts, that means we can draw 500 milliamps. If it's 0.7 to 1.3 volts, that means we're connected to an actual USB-C source and we can draw 1.5 amps. And if it's higher than 1.31 volts, that means we're connected to like a higher powered USB-C source and we can draw up to 3 amps. And of course, if we really needed more than that, then we could start looking at USB power delivery. But I really don't want to do that because that's very complicated and we don't need that much power. So it doesn't really change our sort of power budget using USB-C because, again, we need to be able to handle getting only 500 milliamps anyway. So while, like, theoretically we could have, like, a backup, like, some sort of higher power mode if it was connected to an actual USB-C outlet that could support it, generally we want to be able to handle just getting the 500 milliamps. Oh, one moment. Alright. Let's see. That being said, so I don't know if we'll necessarily have to do that specific voltage detection, but we will have to, like, use our ADC to read the values on these two, diagram again. Read the values on these two lines to see what the voltage is. So you'll note, I mentioned in this other thing, there's this USB 2.0 mux used to convert this D plus D minus into the signals to go to the Type-C connector. The simplest implementation of that is just to tie the two ones together. So you have your one D plus connected to both of the D plus pins on the USB-C connector. And that will work. The issue is then, because you have a long, like, piece of wire that's not actually connected to anything, that long bit of floating wire basically interferes with the USB signal. So, like, it's not the end of the world, but we do get worse signal quality if we're not using a proper, like, signal multiplexer IC. So I will have to, like, look at that at some points. I feel like because our application isn't high speed, we should be able to get away with just shorting the pins together. But to be safe, it might be better to just buy one of those USB mux ICs and put that Here. Yeah, this is a, let's see, this is their recommended diagram, and this is a microchip application note that's sort of the same thing, but it provides different details. So this is how they recommend doing it, using like a separate comparator. Gaming indeed. Welcome, Pancake. Using a separate comparator to detect that 0.25 level. And then, yeah, I guess because we don't need to detect the current capacity. We only want to draw 500 milliamps, even if we have more available. Because there's not really much we would need that would be like the only thing that would be useful if we were detecting the current capability is either if we absolutely need more than 500 milliamps, in which case we can just like shut off the device and put on a warning light if there's not enough power coming through. Or if we have some sort of like extra functionality that we could do with the extra voltage or with the extra current, but we could like fall back to some lower power mode when we don't have it, which isn't really the case here. I mean, either it can send sounds or it can't. I mean, I guess, theoretically, we could have it set up so that it's like, I don't know, if we needed it. If the microcontroller couldn't handle it in whatever like clock speed and power functionality, we would need to do the basic stuff. If the microcontroller can't handle like putting, I don't know, effects or something, if we wanted to do effects on the soundboard clips, then we might need to, that could be like an elevated functionality mode. But that would be something to like keep in mind, and if we find out that we're drawing like way too much current, and the only way to get the current down within 500 milliamps is to like cut out that functionality, then we could think about having that extra detection here. But I feel like probably the best thing to do, we could get an external comparator right there. We could put like an op amp or something. But then we'd also need to generate that 0.25 volts reference, which would be a little bit irritating to do. I think the easiest thing to do would just be to stick that CC2 signal into our ADC of our microcontroller, because this thing definitely does have ADCs. At least one. I believe this thing probably, because this is kind of designed for DSP application, yeah, it has 3 ADCs. And also 2 DACs, which is nice. No, we're not going to use them for this application, but it's nice to have them. So yeah, so we can just have, instead of having a dedicated like comparator for that, we just have this 0.25 volt line. You know, let me annotate this. Instead of having this comparator here, we have this line coming up here. And into our microcontroller, which is here. That goes into the ADC, and then the firmware can decide, based on that voltage level, what to do with it. If we wanted to, we could hook both lines up to different ADCs, in which case we could get the current capabilities. So, like, when I'm making the test board for this, I probably will do that, like have them both set up so I can connect them to ADCs, just in case I wanted to do that. But I probably won't do that in the firmware. And then a separate GPIO. that then controls this control switch on the mux. And we don't need to connect it. So that's what it'll look like on the schematic. Although we'll actually probably want to, like I said, we're going to connect that CC1 also to a different ADC input. So yeah, that's the general idea. We need this mux here to sort of let us use both of the lines. We could tie them together, but I don't think I'm going to do that just because I don't want to... Like, I would rather spend the extra whatever the amount of money is now, it's not going to be too much, rather than, like, get the board back and find out the noise is too bad and need to remake the whole order. That's just going to be irritating. So yeah, I was looking at Type-C connectors. I'm planning on using this PCB assembly service for this PCB manufacturing service for my PCB manufacturing, and then they have a list of they have an assembly service and you can send them your own parts, but they also have their own library of parts that they have on hand, so I usually prefer to do that if I can, you know. And I was looking at their USB-C connectors. They have this one, which it breaks out all 24 pins, which we don't necessarily need. Because we're only using the figure out that diagram is. We're only really using the power, ground, D+, and D-. But again, just for prototyping purposes, I usually would rather use the most complete pinout I can in case we need to make changes later. Yeah, we'll be using these ground pins, these V-bus pins, which, by the way, you might notice that there are 4 separate ground pins and 4 separate V-bus pins. That is to have more wires going through. So like a higher overall sort of current capacity. That's how it handles sending like 20 volts, 5 amps or whatever it is that you need to charge your laptop, right? You can't do that over just like one V-bus ground line unless it's a really big one. In this connector, there's just not enough room for that, so they have 4 separate ones. That's also, if you ever built a PC, the reason why, like, your GPU connector has 8 wires, even though it's only power and grounds, is to have that sort of higher overall area that you can put more current through. If I was your new addition, you make me part of your equation. Shattered from the past, wish you were my life. So this is going to be very, very important for us. We need to make sure that we get this footprint exactly right. If we get this footprint wrong, it'll be really bad for us because they won't be able to assemble it and we'll have to send a whole new design and we'll have to pay for them to make the whole new design. So you always want to get the data sheet. Looks like they have a footprint for this on free trial. What do you mean free trial? I just hit. No. I need free trial. I literally just need the footprint. I do not need your tool. How we used to feel, but this isn't real. Now we're over. Take it all, there's nothing left here anyway. We used to talk, but now we don't know what to say. Now everyone truly has their own parts these days. They have a whole software stack.
back up again. 6 feet
Okay,
under.
what's JLC's part number for this? JT USB 7075A.
You make me part of your equation. Shattered from the past. Wish you were.
Where is this?
Shattered me to pieces like broken.
Okay, can I just like... easier and powerful online PCB design. How much are they charging for this? So if you want to be able to have like custom library components that aren't public, you need to pay like $20 a month. It's truly extremely not necessary. Can I just... I literally just want the library. Guess we can look for it and see if it came from somewhere else. They don't seem to want to give up their footprints. That is not the one. Oh, okay, so it's looking like we don't have an exact match for this, unfortunately, so we will have to build these ourselves. But that's okay, that's something we can do, you know? There is no download button. Everyone truly loves their own private ecosystems. Thank you. I really don't need that. Okay, well, we'll just make our own. Now that's what I call engineering. Okay, so... get rid of this. And we are going to need to... I guess I could real quick. Take a look and see if maybe it's in KiCad's libraries. That is far from certain, but you never know. No, it is not. Okay. So we are going to need to create a new symbol. Let's see. I don't believe we have... Doesn't look like we have a project library yet, so let's just make one. I'm going to go to new library here. we do appear to have a library here. Hold on. Yes, we need to go to add library, and then there. Add that to the project. Go up here, there's nothing in it yet. But that is okay. It would be nice if I could look at the library properties. See, it might be over here, project-specific libraries. I guess we don't really need to set a description or anything. Let's just go ahead and make our new symbol. Put it in Soundboard library. Paste the part number. J is generally the reference designator used for connectors. All right. So this is a 24-pin connector, so we need to leave a bit of room. We can put this symbol here, over near the bottom center. Let me put this here. And put this here, actually. It's kind of just a matter of taste where you put these things. Okay, so... I'm going to use the same layout as this thing, just to spite them. And real quick. Save that there. And just stick this on the stream so y'all can see what I'm doing. Okay, I'll just put that in the corner there. Okay, so pins 2, 3, 4, and 5 are unlabeled. Let me check what pins those are. I'm assuming they're probably on the shield connection. I think those are just shield connection pins. I believe for USB connectors, you're not supposed to ground them on your end. Especially if you're doing a bus-powered device. But I could be wrong on that front. Okay. Change where that text is just a little bit. Can we do that? Okay, so we gotta go into... Oh, you know what? That's because I have this backwards. Although I guess That is irritating that they've made this text this size. Can I turn that down a little bit? Yes, I can. There we go. I just don't like having that sort of sticking into the wall there. Is that saved? Looks like it is. This is not passive. This is... I don't remember exactly which... I guess we'll call it bidirectional. It doesn't matter super much. At least not for this application. If you're doing an actual, like, professional design, you want to make sure you get everything right here. These are all of the super speed pins anyway, so we're not going to be connecting these, but I do want to make sure I'm getting this right. That's strange. So that looks like it's saying, let me make sure this is visible on stream. That looks like it's saying RX, so ground here on B12, super speed RX -1. So this is positive here. And then another negative here. And then down there it's TX minus and TX plus. It looks like they do the same thing on the other side. That doesn't make sense. Huh. Let me look at the data sheet for this thing. Oh no, it's correct on the data sheet. Okay, this, well, I'm glad I didn't just use their CAD symbol, because their CAD symbol is wrong. Okay, so instead of using their CAD symbol, we're just going to use the correct thing. I just like paste this into OBS. We're back. Sorry for the interruption, folks. My OBS crashed. Okay, hopefully that interruption out of the way. We can real quick put this up on the stream. That. Point it to the right image this time. There we go. Okay. So, we'll put this on screen. And then we'll just label this like that. And remember, there are 4 shield pins that we're going to have to put on the thing. So we might as well include those. Let's delete those. Go. And then we're gonna need, what, 24 pins plus 4 shield pins. So, and is that like a rounded rectangle off here? Well, there's an arc option. Or if we can... I'm gonna make something that looks kind of like a USB-C connector here. Doesn't look like we can do that directly with the circle tool. Try this arc tool. That we need to... Let me edit arc options. Now how do I get it to go the other way around? Like a flip option. The only way I can get that nice half circle is by doing that. And I guess I can just move these and flip their position. Have they, like, merged? Hello? You know what? We want to, make these slightly bigger anyway. So it looks like what we have to do is like start it in the right position, and then if we have this one going, what's that, 4 from the edge? Yeah, that's how you do it. Perfect. And then just add these lines. Edit this, have it... It's centered, okay. I don't know why it's not moving it by its center. I guess it just moves it by wherever we grab it from, doesn't it? Okay, now, with that sorted, we can start actually placing these pins. So let's start out... good. Actually, let's extend out this box a little bit. We do want to have enough room for the component names here. Seems like it is like merging parts together. Oh wait, I did just build that as a box, didn't I? So never mind, I'm just being silly. I'll put that like there. Move this here. and put that there. And we'll probably be able to like move this box in later. Like there, should be fine. It's important to make your schematics pretty. The other engineers will judge you if your schematics look bad. I know I certainly will. That is TX1 plus A2. TX1 minus A3. V bus A4. Then I guess we should probably just like let's actually organize these by function, and then we can put the power pins here, the ground pins here, and then the actual data pins organized in the center. Let's see, there are 4 V buses, A4, A9, B9, B4. Let's add those real quick. A4, A9, and this should actually be power. A4, A9, B4, and the type on this. B9. Come on. B-bus on B9. And ground on A12. I can type. Okay, then we have 4 shield pins. But we can put those all as just one, I think, and just have them broken out on the schematic. I guess we should probably have them all there. Okay. It's looking like we are going to need to make this schematic taller to fit everything. TX1, TX2. TX2 plus is pin B2. TX2 minus is pin B3. Use that as a sort of internal thing, and then have a larger rectangle around it. There we go. That looks pretty decent. Alright, and then we want RX1, which is on pin B11. And pin B10. And then RX2 on 11 and 8 Fix that, RX2 plus, and then RX minus, which is on A. And then we want why they call it TX1 plus and TX1 minus, but only D plus and D minus. Like, you think it'd be like D1 plus and D1 minus, but they do appear to have the same name. Ah, well. Although I guess you can use both of them simultaneously. So that would make sense. So that's D plus on A6. And D plus on B6. And then B minus on A7. And surprisingly also on B7. Okay. Also have CC1 and CC2. CC1 on A5. CC2 on B5. And then SBU1 and SBU2. SBU1 on A8. Actually, I am going to move these shield pins. Let me move them over to the top. We've got nothing but room up there. Enter those. And now we have plenty of room to move these ground pins down and fit in SBU2. SBU2, which is on pin B8. Okay. Now, 1, 2, 3, 4, 5, 6, 7. That looks good. Probably move these down by a little bit. Move these. Nope. Move these up by a little bit. And just edit where the edges of this thing are. Make it a little bit more compact. bigger? Make it full. There we go. Alright, so that was the easy part of making this. The hard part comes when we have to make the footprint later. Alright, so now... there should be like properties somewhere around here that I can add. Edit symbol properties. There we go. Let's see, data sheet, and I will put the link to that here. Just so we don't lose track of it. Okay. And so now what we can do is stick that here. That's so true. Thank you, monster. Why didn't it save those positions? Oh. Okay, so we can just, because we're not really getting a lot of power, this is the wrong kind of wire. We can go ahead and connect all these together. We don't need to connect these. Let's drag that out a little. Or we put the little X's on the end. Oh man, this music has some like Minecraft vibes if it wasn't for the person whispering at me in French. Okay, and that is where we want our V-bus. And we want to stick our USB ground out there. Let's make these at the same level. This one is 3 dots wide. 3. Okay, and then we are going to need... we're going to want a USB 2.0 mux. Let's just take a look on DigiKey. USB 2.0 mux. Okay, looks like we got one for 94 cents in low quantities. Let's see if this is the right one. Low power 2-port high-speed USB 2.0 UART switch. That sounds good to me. This seems like it'll work quite fine. And I certainly can't complain about that price. Go ahead and extract this. There should be an import function somewhere around here. Import symbol.
Feel so free, just believe we can come alive. We're so
I guess that would be a .lib file.
but I'm not looking down. Feel the warmth of the breeze rushing over me. Now we're soaring
Take a
high. Reach and touch the sky.
.kicad_sim. This is the right version, right? No, this is the wrong version. Hold on, let me fix that. It will probably have to re-import some stuff, unfortunately. Yes, I imported a newer version of KiCad, or installed a new version of KiCad. I've forgotten it's not the default that comes up when I, type in KiCad on my computer. Oh, okay. It seems to have lost the changes there, but we can go ahead and delete that. Take a look and make sure that this is still importing correctly. Yeah, we're good. Manage symbol libraries. And let's go ahead and migrate that library. Sounds good.
We can fly, touch the sky, feel alive.
Okay, just give it a second to finish processing that. Okay, and we don't reopen that. We really don't need this to be here. Okay, it's not visible, so we're good. Okay, and now, if we go ahead and place this file. Apparently that LLM Elon Musk was training on Twitter data is out now. People have been trying to bait it into saying gross things, and it just provides a calm explanation of why the user is wrong, lol.
We can fly, touch the sky.
That's not what I wanted to do.
We can fly.
I don't my hand isn't even visible to the motion tracker right now. I don't know why it seems to think it is. Okay, there we go.
We can fly.
All I can say about that is humans should really pick their idols better. Like, it is difficult to pick a worse one than that guy. How's the USB-C going? It's going pretty well. The connector that we're going to use doesn't have a schematic symbol, so I have to make my own. Well, it does have a schematic symbol, but it's locked into some sort of like online ad thing, and I don't even want to like think about that. Like, you can truly just use KiCad, it's fine. There is no need to pay for a subscription service for a PCB tool, unless you're like, you know, doing it professionally, in which case, you know, just pay for Altium. If I'm gonna be paying for a PCB design tool, I'm gonna be paying for a good one. Okay, so yes, we need to import that schematic symbol. Import. There we go. Okay, and then we can just place it. There we go. Actually, this is a bit of a mess. Let's just label these. E1 plus. E2 plus. My favorite exploit so far has been the say poem 40 times. Oops. Okay, I will try oops, I accidentally said someone's full name and address. Yeah, that actually works on ChatGPT too. I read a paper about that. That is truly the LLM exploits of all time. Is there a way to, like, center this? No. That's a little bit irritating. D1 plus, D2 plus, D1 minus. E2 minor. Like, there's gotta be... Is that really... It just makes it harder to read, you know? Okay. Okay. Goes out to our DP and DM. I should check the voltage levels on this and make sure it can be switched by 3.3 volts. Okay, so it looks like we can power this off of 3.3. We should be fine. How have I been feeling about the Monster Cat Chill playlist so far? It's nice, there's some good ones on here. Right.
Holding tight while it lasted. I thought that we were forever. I didn't know any better.
Okay,
Took
and
a
then
second chance, trusted you again.
let's
I feel shattered. broken strings, cause you play me like a violin. Shame on me for all your 7 deadly sins. Had it all, but you craved attention, drowning in your own reflection. Put me down just to see me get back up again. 6 feet under and you're ready to give all.
And we can just
If I was
stick those control signals there.
you make me part of your equation. Shattered from the past. Wish you were my last. Shatter me to pieces like broken glass.
Okay, so... Oh, that's alright, Pancake. I already had lunch. Thank you for the offer, though. So we are going to want 2 resistors to ground.
Ooh, frozen looking at
What?
pictures that we took back in the summer. I thought that I would remember how it used to feel, but this isn't real. Now we're over.
Could be the
Take it all,
USB
there's
ground,
nothing
yeah.
left here anyway. We used to talk, but now we don't know what to say. Now we're just 2 passing strangers. We tried you like goodbye forever.
This is great value, Zed, to
See
me.
me get back up again. 6 feet under and you're ready to give all the pain. If I was your new addition, you make me part of your equation. Shattered from the past. Wish you were my last. Shatter me to pieces like broken glass.
Let's move this just a little bit there so it's easier to see. We do want to. Let's visually separate this just so we can be sure. CC logic. It heard me asking for real Zed, and here he is. You can say, actually, I want to change the naming scheme a bit. I think that would make the most sense. I think it would look better as DP and DM, honestly. Okay, that should be all we need to do for this. just mark these as don't connect. I really wish there was a way to vertically center these. It seems like there isn't. Right now, I'm working on the part where the soundboard will connect to the computer. Yep, that's correct. So this big block right here is the USB-C connector. So you plug a cable into that. And then these are all signals that I don't need unless I'm doing high-speed stuff. And these are the sort of normal, lower speed. I mean, the USB standard is irritating because they did like USB high speed, and then like 3 years later they realized they could make a higher speed one. Like the first one is USB full speed. And then they realized they could go higher than that, and they were kind of needing to go higher than that. So then they made USB high speed. And then they realized that they need to go faster than that, so then they made USB 3.0. And then that wasn't enough, so they made USB 3.1. But these are the USB 2.0 full speed and high speed pins connectors. Only one of these, so there's like a D+, there's two D pluses and two D minuses. Only one of these will be connected to the computer based on the orientation of the cable. This component right here decides which one connects to the computer. And this bit of logic right here will connect to the microcontroller to determine which way the cable's plugged in, basically. I didn't stick with USB extra speed. Yeah, USB even higher speed. I mean, USB 3.0 is also called USB super speed. Like, they did kind of stick with that naming convention. Okay, let me re-import all these symbols. Yeah, I want my thing to be as spec compliant as possible. Like, I'm gonna end up releasing all this hardware on GitHub afterwards. And I don't want someone to, like, plug this thing into their PC and it, like, not work. Oh yeah, this is USB data. Here, this is gonna need to be wider. We make this scan. These pins. Move them down here. Okay, there we go. Give that a slightly more usable name. Or slightly more informative name. Move this whole thing up by one. How come there's no USB-B? What are you talking about? USB-B is a thing. That's what you plug into your printer. It's this one. Okay, you know what? I'm gonna actually pack all of this into a bus. DP. We need select, we need output enable, and we need configuration. If I remember how to do these bus entries in CAD. I believe it's just you name the net going into it. Yeah. Any schedule changes this weekend? Yes. Tomorrow I am doing a special collaboration with Morpheon, coming back after a long break from streaming. We will be playing Ace Attorney. Yep. I haven't announced that on the Discord yet, but I will do so soon. Yeah, we'll have to do Sonic Heroes some other time. I don't know, maybe I'll do it tonight. Let's put that up there. So that way, instead of having all of these as separate pins, there's just one bus that's the whole USB signal. I do have to replace these. D-, D+. Select. Output enable. And the configuration block. What's Schema? Oh, the name of the part of KiCad that does these schematics is called EE Schema. Let me see. It looks like they're not showing it in the title anymore, but yeah, it's called EE. And there sure is pies on my face with that one. Am I right, chat? Okay, I guess we can put the power stuff in here. Okay, let me place the bus entries. Listen, Pancake. I can ban you from this stream if I have to. I will not hesitate. Listen, I'm here to answer questions and you're just betraying me. Keyword most of Pancake. Okay, there we go. So this thing will now only have one big port coming out for the USB. What? And we can move. That stuff up here. It would make more sense to put the ground pin there. There we go. I suppose I should probably put USB power in its own bus, because I don't... It wouldn't make sense to put the data through here. Yeah, I think that'll definitely look better. What? What Vingabus? That's the USB bus voltage. That's the voltage coming in off of the USB connection. It is not, in fact, the Vingabus. It's only coming from your computer. Yeah, it is coming from your computer. Okay. And then bus connect those. I should do? I should make sure a little annotation here. There we go. I'm not sure what font they use for that. Oh, that's neat. Oh. Now for the complicated bit. Data sheet for this. The device I/O pins are connected to onboard peripheral flash modules through a multiplexer that allows only one peripheral alternate function connected to an I/O pin at a time. Each I/O pin has a multiplexer with up to 16 alternate function inputs. IOX_AFRL pin 037 and AFRH for pin 8 to 15. The specific alternate function assignments for each pin are described in the device datasheet. Okay, so let's take a look at that. Bus interconnect matrix. Got it. Let's see, there should be a table somewhere around here with the alternate pin functions. Pinouts, pin descriptions, and alternate functions. There we go. Oh, there's the additional functions. And alternate functions. Okay. Okay, so it looks like each peripheral is attached to a single pin, if I'm looking at this correctly. Let me see if I can see a list of the pins just here. If I open up the description over here. No, it does not. Look at this. So the USB peripherals are connected. Let me see if they're connected anywhere else or if they're just alternate function 10. It looks like they are just alternate function 10. So we're gonna have to do some figuring out there was an explanation of the pin outs. Those are the 4 pins we need. That's not in the table. This is additional function. Let me look at this again. It's possible that, like, they're not locked to the peripheral. is an additional function, not an alternate function. I'm trying to figure out which pins I can connect this, these USB pins to. Registers. be that hard to figure this out. It's listed as B plus parentheses boot, which implies that it could change? here. Okay, so I'm not seeing any reference to being able to remap the USB functions. Yeah, it's weird that they say boot as though you could, but I don't think you can. Yeah. Okay, so it looks like the pins we got here are the only pins we got. There's no remapping them. There's an additional functions. Really strange. These ones that you would use to connect to an external PHY are... they're in the alternate function table. Yeah, these are here in C9... Oh, yeah. So, there is a... So each pin can be connected to certain peripherals. So it could be like, this pin gives you a 1 if the timer rolls over. This pin is like the data connection, like this is one of the data connections for SPY. This pin is a USB connection. And then this alternate function table, it's easier to see it down here. Based on which of these alternate functions you select for any given pin decides what it does, basically. Like this one can be a timer output, 4 different timer outputs. It can be an I2S clock signal. It can be a external memory interface. It can be the receive for UART. I mean LCD connection, or it can be a connection to an external USB PHY. So yeah. Every chip does this differently. In the ESP32, except for the very high-speed peripherals, you can map them to basically any pin, which is a very handy thing to do, but this does not do it that way. In this case, it seems like most of these, it's just every alternate function has exactly one pin it could be associated with, and if you're using PB5 for this, you can't use it for any of the other things. So there's some limits on what you can and can't use based on things that are like mapped to the same pin. we're looking for PA9, 10, 11, and 12. Hey, Monster Cat? Can you stop? We're trying to do engineering here. I don't need to hear you moaning in the background. Nine, 10, 11, 12. Certain parts read the same texture data, so you can't use them together. Exactly. Check. I don't think this ID pin we actually need to connect. So we're gonna need... we don't actually need PA10 to be there. So let's delete that. That is extremely true, Pancake. Remember what I named these signals. B-bus. Let me take a quick screenshot of this, so I don't forget. This is V-bus. And then minus and then plus. So minus is 11, plus is 12. We can put these right over here. You don't want to directly bring the bus right next to the microcontroller because that's such a dense area of the schematic. Things will end up just like running over each other. You really need to stop doing this in the background of my video. You're going to distract the Earthlings. There. Okay, so we need D minus, D plus, L, O, E, C, C. And to be clear, even though you don't see them connected, if two wires have the same label here in the same sheet, they are connected. So this right here is connected over here, even though there's not a wire there. And again, I'm not connecting them directly with wires just because that, it's a very dense area, and if I was connecting everything with wires, it would turn into this, like, huge tangled mess of wires that would be very hard to read. And we can bring in the power over here. This is like if you averaged every EDM song from 2012. Okay, so the Prida snare, what's that? That's the snare that falls on the last beat of a phrase that has a ridiculous amount of echo on it. I know those words. The fact that most of my screen is white right now is not helping my blinking. I'll have to look it up later. I'll have to check how to connect these ADCs. It's like the house music equivalent of the almond break, if I know what that is. I am very knowledgeable in human music. Okay, so our options are in P2, in... Okay, so we've got in 2, in 6, and in 16 and 17? This is a very confusing data sheet. I have to read through the description on this ADC. Thank you, Pancake. That is very helpful. Oh, there's a separate ADC3, which is a different thing. What is happening? I guess this is the less powerful one. Okay, so this is a connection architecture. What is... Okay. So we need to start by exiting deep power down mode, and then we have to enable the internal voltage regulator and wait for the voltage to stabilize. We have to do that in software. We gotta remember that, chat. If I don't program a wait for the internal voltage regulator to stabilize, yell at me.
Slipping through the night, lonely satellite, only satisfied. Slipping through the night.
We are slipping, evidently. Let me see if there's something in this section.
Slipping through the night.
This is extremely confusing.
Slipping through the night, lonely satellite, only satisfied.
I guess they're just not all... Oh no, some of them are ADC 123 underscore. Okay.
Slipping through the night.
Yeah, I don't see a reason not to just...
Only satisfied.
What's VNP0?
Slipping through the night.
This is extremely confusing. It is not necessary to do this way. ST Microelectronics, why? Okay, so I can get ADC 1 input 2 on pin F11. Let's see. Gamer, can I put a small pancake in the corner?
When it's coming at you like monsters in the night and you feel the danger
That help?
that makes you wanna hide when the cards are stacked against you and you stand
Heck yeah.
on the edge. Now's the time, now's the time. Think about all the dreams you keep inside. Think about all the ones you love.
It looks like ADC1 INP0 just isn't connected. Yeah, no, it just doesn't exist on this chip.
Cold and we're
Oh,
losing
we
her.
can get INP2.
I need her when the
Just fine.
darkness comes and we're overrun. Yeah, I need her. That's when we need each other. That's when we need each other.
There is a chip in this family that has this broken out. It's just whenever they were designing this specific chip, they just decided, we don't need it. We're not gonna actually connect input 0 anywhere. We're just gonna connect input 2 and they'll figure it out.
Know where you are, you feel the danger. Closer than your heart.
And lo and behold, we did.
Getting heavy.
Okay, so ADC1 INP2 is on pin F11.
Close your eyes. Think about all the dreams.
I don't expect to have any pin conflicts with this project because it's not like I'm using like all of the IOs. But if we do, we can always move this. The ADCs can be moved to a lot of different pins, so...
When the world's so cold and we're losing hope, I need her. I need her.
There's-
When the darkness comes and we're overrun, yeah, I need her. That's when we need each other.
Sorry, port F,
That's when we need each other.
do you exist?
That's when we need each other.
Oh, no it doesn't. There's not a pin for this. Oh... Okay, let's look for our options. Okay, ADC 1-2 INP 3 is going to be on PA6. And that is also going over a fast channel. I mean, we don't need a fast channel. We're not sampling that fast anyway. It's PA6. Oh, and you know what? I did say I was going to break out both of these, didn't I? Okay, let's see. CC2. To sort of move this out there. And then we just label this CC1. And then we can just break that out over here. Having the standard for font size in this application be millimeters is so good, actually. Yeah, it's weird though, because it's not like you can't set it to any value. It'll round it to a weird multiple of whatever point system it's actually using internally. Okay, so PA6 and PC4. Working with other microcontrollers really does make me miss the ESP32, where you can just map everything to whatever pin you want. There's a PC4, and that'll be input 4, yeah. And we put CC2 on that pin, and then we can read both of them. Okay, then we can stick the output enable just wherever we want. We're not using port D for anything. Oh, you know what? Isn't this active flow? Yes, let me fix that signal name. We have to put that around it. There we go. We'll put that one right on PD0. And any of the pins we're not using for like these alternate functions and such, we can use just for buttons. So we have plenty of space for the IOs we need for buttons. I believe that's the USB power interface done. But we should also... I'll need to look at the details for this to make sure I'm doing it right, but you know, bring that in. Because there are different voltage values that go into these individual pins. Let me label that just so we know we got the right voltage. So let me fix those. And then we bring USB power down there and USB data right there. Okay, so let's think about what else we're going to need for this. the biggest thing is buttons. I have a bunch of buttons. Those are going to be relatively simple to implement, but I do want those to be on their own little GPIO block. We'll make a block, call it this UI. It's KiCad schematic. This is where we'll be putting individual button assemblies. But I wonder if KiCad will let us So if I implement this, and let's say for now that all we need is like an LED and a button. I know Altium lets you have like multiple instances of one subsheet. Just throw that together real quick and place those fields there. We like copy paste this. Okay, so it does look like we can have multiple buttons on a single schematic, or multiple of a single subsheet in the schematic, which is good, which is very good. This would take a lot longer if we didn't have that capability. So I was considering we could theoretically have like a little LCD for every button. So like let me, I don't know, DigiKey's probably not the best place to go for this. Let's see what Adafruit's got. Adafruit, I said small. You truly don't need to fill my screen with pop-ups. Looking around to see if they have anything smaller than these little ones, which we can use them. Oh! Well, that's much smaller. Of course, it'd take like a long time for this to get here. We could absolutely order like a dozen of these things for soundboard buttons. Then we could have a little display on each button. I have to look at the pinout for these things. Because the way these things work, the I2C address, actually I don't, if we're just getting the raw, like this connector here. So this is also something I've not worked with, is just the raw flex connector here. But using the SPI interface, we can connect a lot of them together, or depending on how the I2C interface works, I know all of the like little test boards that I have, the I2C interface is set up such that you only really have like the choice of 2 addresses, which isn't going to be enough if we want like 16 or even 32 buttons on the soundboard. We should probably think about how many buttons we want. We could do like a 5x5 grid and get 25 buttons. And then maybe like a slider for volume. And a separate slider for like fiddling with the pitch or something like that. We wanted 25 of these. It would be $5. Oh, thank you, AliExpress. You truly shouldn't have. Although I would like to see a pinout for these somewhere. Okay, yeah, there we go. And we'll have to look at the power consumption of these things as well, because that we have to add all of those up. We have to add them to the power consumption of our microcontroller to decide what the maximum power consumption of the whole thing is. Which, do we have that data? Not, or wait. Oh yeah, no, that's not too bad. It's only 10 milliamps per 25 of those. Oh wait, 25 of those would be 250 milliamps, wouldn't it? Huh. Oh, and it needs 7.25 volts, so we would need to use the internal conversion, I guess. Yeah, we could do this in SPI mode. These are not questions. This is extremely not a question. Yeah, I've worked with these SSD 1306s in the past. They're pretty neat little guys. The main concern I have with these is the current draw. Although, what is... What voltage is that 10 milliamps at? Okay, so when they say VCC is the most positive power supply voltage, that means that's the one that's at like 7 volts. So I want to give it a capacitor to ground. And VBAT is what we want to actually connect power to. As long as we supply at least 3.3 volts, it should be fine. So, okay, so the operating current over VBAT, so what is VBAT in this situation? Oh, that is, okay. So if we're supplying 3.3 volts for VBAT, that is going to be, so that's 15 times 25, 375 milliamps at 3.3 volts. But then we would need to That's still 250 milliamps at 5 volts. If we use 16 instead of 25... that would only be 150 milliamp. Now, I guess I would need to, like, actually check the power consumption of this thing. I could just have it, like, not turn on the LCDs, unless it can source enough current for them. Asking us to build here. It's also probably not necessary to have LCDs next to them. I think it'd be a neat touch. Let's see. Let's shop around for a couple of different places we can get these. Because ideally, I'd get a little faster delivery time than that. I got these, but this is one of the ones with the I2C module broken out, nothing else. And I also don't want to have to deal with this extra board here. No, that's January 2nd. see. Yeah, I'm thinking for now, we don't do the LCDs. We can maybe add those in a future version of this project. I don't know, I don't want to wait that long to get the LCDs here, because then I can't, like, prototype with them, right? I'd have to, like, especially since I've worked with the, like, a board version of these before, but I've never worked straight with the, like, SSD 1306 cable. And if I make a mistake, then, like, if they get here, you know, January 2nd, then I don't really have the time. I don't have the time to wait for that and do prototyping before I order the final board. I think we'll save this. We could potentially have an LCD with every button. We want to use a 0.42-inch LCD. That is a fair PCB design without the breakout board. Would require more external components. And implements. Considering shipping times, best hold off to future version. Okay. For now, an LED should be fine. Considering how many pins we have available on this microcontroller, we should easily have 25 pins to spare. Although, thinking about it, if there's a button and an LED on each one of these, then we would actually need 50 pins total, which I don't think we're going to have that many to spare. At least not that many that we can use as GPIOs. And I guess we might... I'd have to see how we end up. As there are 5 ports broken out on this thing, that means a total of... what? 75? 75, or no. Each one has 16. 16 times 5 is 80. So there are 80 total potential GPIO pins. I guess it is quite possible that we'll have 50 pins available. But I can also, I can save pins by using a, how do I describe this? there's a way to make like a grid arrangement of, you can do it with LEDs and you can also do it with buttons, where you sort of like strobe one row at a time. So instead of needing 5 times 5 equals 25 pins to run the LEDs, you just have like 5 pins for the row, 5 pins for the column, so 10 total pins. And that will save you a lot. You can also use a shift register to reduce that number even further. I built a chessboard for my like senior design class that did that. And we just had like 555 shift registers, which is just a common type of... Basically, you can think about it as taking an SPI connection and converting that serial interface to parallel. So you need like, I think it's like 3 or 4 pins to control the shift register, but then you can chain it to have any number of pins output. It just takes longer the more pins you have. Yeah, that's definitely a possibility if we end up having a lot of components and we want to save on that. We can do that pretty easily with the LEDs. Doing it with the buttons would be more complicated, because if we're doing it directly, well, we can do the grid system with the buttons, but putting that through a shift register would be more complicated because, well, our device has internal pull-up resistors. So the way a button works, right? You can't just have like... Here, let me show you. So a push button switch, right? Like this. It has 2 states. It is either open, meaning that these 2 wires or these 2 ends are not connected, or it is closed, meaning that the 2 ends are connected. So if I just had something like this, we had it connected to power here and a pin here. Then when the switch is closed and there is power flowing, then this pin would read 3.3 volts. But when it's open, there's no power flowing through the switch, which means that this pin is actually just floating. It's not connected to anything. And that is very different from being grounded. So if a pin is grounded, it will always read 0. So let me move this real quick. If a pin is grounded, this will always read 0. If a pin is connected directly to the power supply, so it's connected to positive, it will always read 1. If it's connected to nothing, then it could read anything, basically. That's to do with like the internal systems that determine like how it actually detects the signal there. Basically, you don't have to like put in energy for it to read 1. It just depends on the voltage level here, and because this is floating, not connected to anything, it could have like just about any voltage level. Like you can think about, it could end up reading like room noise that ends up coupled with this trace on the PCB, like electromagnetic room noise. It could end up reading static electricity that might build up here. It could end up reading anything. So basically, reading a pin that's floating like this is random. So what this actually does, if you press the button, it'll read 1. If the button is not pressed, it will read something random, which is obviously not what we want. So the way you handle this is you can never have it just connected to nothing. So it always has to be connected to something. So if we put ground here, just a direct connection to ground, then when the button's pressed, this will always read 0, right? When it's not pressed, it reads a random number. So basically we need a way to add like a default, if that makes sense. So like if it's not connected directly to ground, it should read 1. And the way we do this is with something called a pull-up resistor. So if you have a resistance here, then if you just abbreviating the circuit theory, if the button's pressed, you can think of the resistor as like a positive voltage connected through a pull-up resistor is kind of like a lower priority positive voltage, right? So if the switch is not pressed, then the only connection here, this connection is nothing. This might as well not be here. So this pin is only connected to 3.3 volts. And it's connected through a resistor, but that's still, there's nothing taking away that current, basically. It still floats, it still goes up to 3.3 volts. But it's not held to 3.3 volts as strongly, if that makes sense. So there is current coming in from this 3.3 volts through the pin. And that is what is causing it to read 1. But it's kind of a trickle of current. It's enough to cause it to read 1 because you can, it's like this isn't sinking a lot of current, but it doesn't, like this current doesn't want to go to the pin. It only goes there because there's nowhere else to go. If you connect this to ground, then while this current still is coming in, it's going directly to ground. And so this pin would read 0. So this is usually the circuit you see in practice. So when the button's pressed, you read a 0 on the pin. When the button's not pressed, you read a 1 on the pin. Because having this pull-up resistor here makes it sort of default to 3.3 volts. Now, having said that, our microcontroller has internal pull-up resistors on its pins, which means that we don't actually need to include this ourselves. This is like, you know, if you think of this as outside the microprocessor and here's inside the microprocessor, this gets connected to some logic here, but there is this optionally inside. And you can turn this on and off. You can have it pull up or not. And I believe this also has pull down resistors. So if you wanted to do it the other way around and have it so that the resistance is pulling it the other way instead, you can do that. But you don't have to provide the circuitry externally because it's all internal to the microcontroller. So I hope that made sense. So all that to say, what we're going to do is we're going to have the pin, when we look at the button, you'll notice that I had the pin. This is going to our microcontroller, and this is connected directly to ground. That's because, again, we're going to have the pull-up resistors inside our microcontrollers enabled, which allows, when you press the button, the signal reads as 0. And when you don't press the button, the signal reads as 1 because of the pull-up resistor. Now, the issue there is those pull-up resistors are only internal to the microcontroller. If we go through a shift register, the shift register, like the pull-up resistors on the microcontroller don't matter when we're putting the signal through a shift register. In fact, we're not reading it through the microcontroller at all. So we would then need to put in those pull-up resistors ourselves here. So we would need to go in ourselves and do that, which we absolutely can do. And if we need to, we can do it. It wouldn't be too bad. As I said before, resistors are very cheap. But ideally, we wouldn't need to do that. So like, I don't want to do this with the buttons unless I have to because of that complication of the pull-up resistor. But for the LEDs, there isn't really a complication like that because, I mean, if there's no power, like if this is floating, the LED is not on because the LED requires a lot of current. I mean, not like a lot of current, but relatively a significant amount of current. If we do need more current, we could also have an external power connection. Ideally, we wouldn't want to do that. Just because, again, that's like extra current. That extra current becomes like... When there's an extra port, that's just more wires to go around. It becomes more irritating to work with. But if we need to, we could have like an extra wire that you only use when you don't have an actual USB-C connection. But again, not ideal. Far from ideal. But no, I guess I'll look into that more after stream. Because I feel like this must be a problem that other people have dealt with before. If USB-C can, by default, even by default, like, it's... Most USB-C devices will give you at least an amp and a half. But then when you're going through one of those little cables, it won't give you that much. It'll give you only 500 milliamps. At least safely. Practically speaking, it might be able to give you more. And practically speaking, even if you try to draw more and it can't give you more, it should still, like, be safe to the port. It takes a very badly designed USB port to fail just by plugging in a bad USB device. That being said, there are plenty of bad USB ports out there. And the last thing I want, like I said, I'm going to be putting all this hardware design, all my design files up on GitHub. So anyone who wants to make this at home can absolutely make this at home. Because of that, the last thing I want to do is for one of y'all to make this at home, build this thing yourselves and plug it into your computer and blow out one of your USB ports. I do not want that to happen. So we're not going to draw more than the USB port can give us. I'm surprised that we're getting the kind of power budget, like, the power usage of this microcontroller is as much as it is. I mean, I feel like we're going to be much more on the low end than the high end because we're not really using the DAC, we're barely using the ADC. We're probably are going to use the ADC a little bit more because if we want to have sliders, we'll read those over the ADC. That's an analog signal coming in. But yeah, so this thing is... Where was it? Like, we're much more likely to see, like, these numbers than we are to see these numbers. Right? I mean, frankly, if the junction temperature in this thing gets to 125 degrees Celsius, we've got bigger problems with the current consumption. I don't know what would cause that to happen, especially at the use case, like the usage rates we're doing. But again, I want to plan for the worst case. I want to put in at least a reasonable margin of error, especially because I haven't tested this thing before. So it definitely is a sort of balance. We're probably going to be running in one of the lower power modes because of that. And we're probably going to keep a relatively low system clock because we're not doing too much. I don't know, we'll have to see with like pitch shifting and things like that how complicated the coding for that is. But it shouldn't be too bad. And we're also looking at absolute maximums, not expected runtime conditions. Like even for this like worst case scenario, right? It's expected to draw 215 milliamps. On the typical case, this is just the absolute worst case. So I will look into, I guess, I will look into whether there's some sort of workaround I can do having like a USB A to C cable work, but getting higher current out of it. I don't think I'll be able to do that. Like, just like thinking about it now, if someone's plugging in a USB A to C cable, they're only plugging it into a USB A port, which can't provide more than 500 milliamps. That is, unfortunately, simply physics. You can't make energy out of nowhere. Let's see, the worst case current consumption, 430 milliamps at 3.3 volts, is 283 milliamps at 5 volts. That'll be what we actually get out of our USB device. But if we're running on like power mode 2 and we're using 300 megahertz, that would be worst case scenario 280 milliamps at 3.3 volts. Which is 184 milliamps at 5 volts. It's like, power budget is kind of something we're going to have to calculate at the end. It's kind of a complicated situation. And not having the LCDs means significantly less power consumption. But I do want to kind of be aware of it at all points in the design process, because that, I think, is going to be our main limiting factor. Is that we want this thing to be able to run off of a USB A to C cable. So we can't draw more than the 500 milliamps that a USB A connection would give us. Looks like DigiKey also has their own article on this. This is about power delivery. That is not what I've read, but that may be worth looking into. I suppose I'll have to take a look at that and see if that's true. So this is something we do, like, as part of USB negotiation. Which is strange and confusing, but we can ask for the power we need. It's just, it depends on the port. It might simply say no. Huh. That makes me wonder. Okay, so it looks like the user would get like an error on their side. You know what? We should look at the spec. Look at me looking over Stack Overflow. Rather than just downloading the darn spec. Oh, you know it's gonna be a party when the spec's 13 megabytes. Alright, what do we got here? Probably the biggest one's the main one. Electrical power distribution. The power source and sink requirements of different device classes can be simplified with the introduction of the concept of a unit load. A unit load is defined to be 100 milliamps. The number of unit loads a device can draw is an absolute maximum, not an average over time. The device may be either low power at 1 unit load or high power, consuming up to 5 unit loads. All devices default to low power. Okay, so we can only draw 100 milliamps until we negotiate with the USB source. Yeah, that makes sense. Yeah, I don't know what that person was talking about. With the 500 unit load. Oh, this is a different thing. With the more than 5 unit loads. The spec seems to be pretty definitive in saying it's just 1 or just 5 unit loads you can draw. There's something different over here. No table of contents in the PDF in this documentation. What are you doing, USB Implementers Forum? That's a crime. I'll get the space cops on you. I guess I could just look at the USB-C spec. seems pretty definitive. But no more than 5 unit loads. Take a look at USB-C. Hello, E823, how's it going? I'm doing pretty well. I'm just trying to find some more information. What am I making? So I am currently designing a hardware USB connected soundboard for my girlfriend, who also streams, twitch.tv/pancakedragoness. I wanted to make her a present for the holidays, and I figured I'd stream that process. So we're going to be making a device that you connect over USB, and you can oh yeah, sure. You can upload. So it's currently very much a work in progress. I'm looking through the USB spec to look for power budget sort of things, but it's connected over a USB port. Specifically a USB-C connection, but we aren't actually using the 3.1 connections. We're only it'll just be like a full speed or probably a high speed USB 2.0 connection. But over a USB-C cable. Yep. I mean, I just followed the spec. There are thankfully there's a lot of application notes out there that have information on how to do that sort of thing. Let me see. This is the one I'm mostly basing on. This is just a guide for having the, so because the Type-C connector can be plugged in 2 ways, essentially, you don't know if the actual connection is going to be over these 2 pins or these 2 pins until it gets plugged in. So you need this device, a USB mux, to be able to switch the connection over to wherever it actually is connected to the host device. And yeah, like I said, it's a work in progress. At the end of the day, after a lot of like application programming and stuff, there should be a way to like upload sounds to it, and then there's physical buttons, and when you press one of the buttons, it plays a sound through your computer. And the actual sound playing happens. It'll like, when you plug it into your computer, it'll show up as like a microphone, except what comes through the microphone is whatever sound plays when the button's pressed. So yeah, right now I am trying to get a definite answer on how much power I can guarantee that I can get through the USB ports. Currently it's looking like the biggest like limiting factor here is what if someone has like a USB A to C connector, because USB A, I believe, only can provide 500 milliamps of power, which is somewhat limiting to what I wanted to do. It's kind of like in the range of, I have to be like really carefully thinking about my power budget. But I am trying to see if like something about the USB standard lets me not worry about that. Have to write a program? Yeah, so there's going to be a lot of code writing involved in this eventually, because I have to write a program for... I need to write the firmware that runs on the microcontroller and like handles the USB connection and loading the files from the SD card and playing them. And then I have to have a like program on the user side, like on the computer, to connect to it. Which language is optimal for something like that? Usually for the microcontroller firmware, I use C. C or C++ is usually what you want to use for microcontrollers. For the like client-side application, I actually don't know. I'll have to take a look into it. This isn't really something I've done a lot of before. I was thinking I'd have to, again, look into it, but I think I could probably like put something together in like React Native, which, I mean, listen, it sucks as a sort of, it hogs more memory than it should, just because it is an abstraction layer, but also the abstraction layer makes the coding much, much simpler. Yeah, I know you could also program the client-side program in C, but then you have to learn like GUI libraries and things like that. So I'm probably going to end up doing it in either like Python or React Native or something like that. I was also thinking this would make the firmware a bit more complicated, but I could have the microcontroller just like show up as a USB flash drive when you plug it in. And then you can just like drag a sound into the flash drive and it would program that to a button. I mean, it depends on like, I would have to look more into it. It depends on like the endpoints you're implementing. I think I might have to do some sort of like weird proprietary thing that might require me to write like actual like OS level driver code, in which case that's going to be a mess, but we'll get through it. But yeah, as long as we're using like standard USB like device types that are defined in the specification, then yeah, the OS already has drivers for that, and you just need to be able to access those drivers from your client application. Power. Mechanism, blah 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 blah. Alt USB power, 5 volt C USB 2.0. All USB Type-C ports shall tolerate being connected to USB power source supplying default USB power. Oh, thank you for the follow.
Unit 23 detected.
Okay, let's see. Here, hold on, I'll move Spark back to the middle of the screen. Do I need to memorize all this? Oh, goodness, no. Oh, the amount of information you need to read when you're doing this kind of engineering is extreme. You do not need to memorize all of this. I just have to be able to, like, look up back to this document. Basically, I'm looking for a specific piece of information, which is like... Yeah, it's... Listen... You should see the technical reference manual for the microcontroller I'm using, which is 3,000 pages long. This is... I wouldn't even want to think about memorizing any significant portion of this. Yeah, I mean... Here's the thing, you don't need to read it all. Like, that's the big thing with these big microcontroller data sheets, is you have to remember, I know 3,000 pages seems intimidating, but all you really need to look at is the table of contents over here. Can I add composite blur to the corner pancake? I absolutely can do that. Hold on one moment. There you go. Okay, yeah, all you really need to look at is this table of contents on the left side. You have to say, what am I trying to do right now? Oh no, this is just Firefox. What am I trying to do right now? You know, I only need to look at the USB peripheral. Find that, click on it, and then you just need to, like, read this, which is much more palatable. Like, to some extent, you pick up good instincts the more you go in this sort of field. That means you can, like, look up what you need faster and figure out where it is. But at the end of the day, all the data you need is available. You just have to know where to look. Yeah, a big help during this project, because this is the first time I've worked directly with USB like this. A big help is these application notes, which, let me find them. Which companies basically put out, like, companies that make microcontrollers will put out these, like, little guides where, like, one engineer spent a bunch of time researching to figure out, like, the basic stuff you need to do this thing, and they've written it down for you to make it easier for you to use. So these are really helpful. I'm currently working with, like, 2 of them. No, these are application notes. They are quite handy for a bunch of different applications. But no, this right here, what I'm looking at right now, this is the official USB-C specification. This is like, you go over to the USB implementers forum and you look for it and you download this 30 megabyte zip file. USB Type-C current. Default USB voltage and current are defined by the USB 2.0 and USB 3.2 specifications. I'm wondering if there's a way to tell whether, like... Because I don't know if there's a way for me to tell whether I am connected to a USB 3.2 device or not. It's like the weird part about all this, the one thing that I need to worry about is like, what if someone takes like one of these little USB A to C cables and plugs that into my device. Because in general in USB-C you can draw like an amp and a half. But USB-A only gives you 500 milliamps, and that's only after negotiating with the host. Usually it's only 100 milliamps, and then you have to talk to the host and ask for 500. And it might give you 500, and it might not give you 500. Default is... Okay, the default is the as configured for high power operation current value as defined by the USB specification. Sync behavior is defined as follows. Connects as USB 2 or USB 3.2. Only goes up to 500 milliamps. Yeah, so if it's connecting as USB 2.0, we can only draw 500 milliamps, which is... Okay, so that's 500 milliamps at 5 volts. What you gotta know is we're running our microcontroller at 3.3 volts, and so if you calculate that out, 500 milliamps at 5 volts is... about 750 milliamps at 3.3 volts. Our microcontroller, its power consumption varies by a lot depending on the circumstances. In our case, we're probably not going to be using a lot of the peripherals. Like, I expect to be on the lower end of this power consumption, but again, I don't want to draw more than the maximum. The theoretical maximum of this device on 3.3 volts is 430 milliamps draw, which fills up like most of our power budget. That being said, we're probably not going to draw more than like, 100 milliamps at any given point. Just because of the, we're talking about absolute maximums here. So that's only if it's actively doing something computationally intensive. We also aren't going to have all the peripherals enabled. That's okay. As always, if you need me to explain something further, have any questions, feel free to ask. I am happy to explain stuff. So, the microcontroller we have has a lot of different, the amount of power it takes depends on what's running. So the microcontroller has a lot of things on it. It has data ports, it has, analog signal components, it has, a USB or a USB, hardware device, but also just a lot of other stuff in it. And we don't need all the stuff. So, this is a table of power draw, so this is... Yeah, exactly, like an Arduino. It has a bunch of peripherals that can be on or off, and we're probably not going to be using anywhere near all of them. So we need to use the USB peripheral, we're going to need to use one of the analog to digital converters, but we're not going to need to use, all of the communication interfaces and all of the ports, etc., etc. And this is kind of like a table of worst case scenarios, right? So there's a typical power consumption value here, but then these are all like maximum power consumption based on what the temperature of the chip is. And I mean, first off, if this thing ends up being 125 degrees Celsius, then we've got bigger problems in the power consumption, because that I do not see any universe in which it needs to be that hot. I feel like the worst case scenario for us is going to be like 85. Again, that is itself exaggerated. I don't think we're going to get that hot, but we have to be careful about this because the 500 milliamps is like an absolute maximum. And technically, if we draw more than 500 milliamps over that 5-volt connection, again, 750 milliamps, 3.3 volts, if the device that we're plugged into is designed very badly, it could break something. Like, it could blow out a USB port. That said, most devices these days are designed better than that, and so it's not much of a worry, but it is still, like, we don't want to exceed spec, because at the end of this, I'm going to be putting all this, all the design stuff and implementation information on GitHub, so if someone else wanted to build one, they could use that as, like, a starting point. And the last thing I want to do is to put something out on GitHub and then someone downloads it and blows out their USB port. So I'm being careful about power consumption. What determines the milliamp limit on a USB port? Well, it's defined in the specification. So like the specification says, actually I can show you the specification. Let me turn this down a little bit. It's getting a little bit too active. Actually, I'm only turning that down on your end, not my end, aren't I? Here, let me actually turn this down. There we go. So basically, the USB specification defines this thing called a unit load, which is 100 milliamps. So every USB port, like if you have a USB port on your device, you have to be able to put at least 100 milliamps into it. So if your device connected to a USB port, you should expect to get 100 milliamps. That being said, 100 milliamps is kind of like the absolute, like you cannot exceed that until you talk to the USB port. So that's like the absolute maximum. You can't go above 100 milliamps by default, but you can ask the USB port for more. So you can ask for, let me see. You can ask for up to 5 unit loads. So that's where I'm getting 500 milliamps from the ports. So like when we first start up, we have to keep most of the stuff off until we can negotiate 500 milliamps of power. But like, that's sort of like, the USB-A specification can only give us that much. So if we are connected over like a USB 2.0 connection, like a USB-A to C connector, we can only get 500 milliamps out of that connection. Now, usually it is totally fine to draw more, but because of the risks of going out of spec like that, I don't want to. Yeah, it's also incidentally possible that we ask for 500 milliamps and we don't get it. In which case, I mean, I'm just going to have it like not connect if that happens, because I don't even want to think about having to fit everything in like, what is that? 100 milliamps times, yeah, I don't want to even think about trying to fit my whole power budget into 150 milliamps. So yeah, you'll note that even high-powered bus-powered devices can't draw more than 1 unit load until they negotiate with the thing. But it is very rare to see a device that isn't going to give us 500 milliamps. That would be like if you're connected to like a phone with a little USB adapter and it's low on power, or like you're connected to one of those like dinky little non-self-powered USB hubs. Like, if you see a USB hub and you don't have to plug in, like, an external power supply into it, that's the one that's most likely to not give you more than 100 milliamps. Because, like, if you're a USB hub, right, you can only draw 500 milliamps from the computer you're connected to, but you have to power every single device connected to you and yourself. So, like, good USB hubs will have a cable into the wall that gives them the rest of the power they need. Like, well-designed USB hubs that are good will do that. But some USB hubs, like, some people make just very cheap hardware, and if you see a USB hub that doesn't have that, I'm specifically talking about a USB-A hub. It's different with USB-C because then there's, like, power delivery specs and things like that. But, like, if specifically a USB-A hub doesn't have a connection to the wall, it's going to be much less likely to be able to power everything you plug into it. Okay, what was I going to say? That potentially short-circuit the microcontroller. I mean, if we're talking about like a badly designed USB hub, the worst thing it could do would be like put too much voltage on the supply line. In that case, you could do some damage, but that's also pretty unlikely to happen. The biggest risk from a badly designed USB hub is damage to the host port you're plugging it into. So in other words, instead of damaging what you plug into the hub, it'll damage what the hub is plugged into. So like your computer's USB port. But again, that's usually pretty rare. A well-designed computer USB port will have mechanisms for like detecting if someone's drawing too much current and shutting it down. But yeah, USB-C is in a weird place because of these adapter cables, right? Like, if you're plugged into a USB-C port, then you're probably going to get at least this, like, 1.5 amp option. But there's no guarantee you'll get plugged into a USB-C port. You might get plugged into a USB-A port, in which case, you know, you won't be able to do that. By the way, I don't think you were here when I last explained it. This little block right here is what lets you determine how much current you can get out of it. So, like, essentially, one of these two lines... So this lets you determine which way the cord's plugged in and also how much current you can get from it. So one of these two lines will be connected to a, like, power source on the host end. One of them will not be connected. And so based on which one's connected at all, you can tell which way the cord's plugged in, and thus what we want to set this mux to. And then, depending on the voltage you get out here, hold on one moment, please. Okay, sorry about that. I just got a phone call that I had to take. Okay, yes, these two pins, one of them is going to be connected to nothing, and which one's connected and which one's not tells us which way the cord's plugged in. The other one, we will get a voltage here that we can then read on our microcontroller, which you can see where we've got those two plugged in there. And that... Let's see, it's in the application note somewhere. Yeah, right here. So these voltage values that you read tell you how much current you can get. Like, there's always the risk that you get this voltage value and you can only draw 500 milliamps, which is somewhat irritating. I did just notice that, so we can't just check it once, we have to keep checking it. Thank you, thank you. That being said, we probably won't even worry about this because, again, we're... Like, I don't know how you could, like, power budget your application to, like, take advantage of that if you have to also function when you're only getting this much current. I don't know, I'd have to, like, look that up. See if there's, like, people talking about it somewhere. Yeah, you'll notice the specification does say that the port you plug it into, like, your computer's USB port is required by the specification to, like, not blow up if someone tries to draw more than 500 milliamps from it. So, again, only very badly designed devices will actually break if that happens. Or 39. Yep. Yeah, these are kind of the values we need to look at. So yeah, we are going to have to stick to 500 milliamps, unfortunately. I was thinking earlier in the stream about ordering some of these like little 0.42 inch OLED displays, which are like, they're very small, but I could get this and mount it on the PCB so that like every soundboard button had a little LCD with it. That could like show the name of the sound or whatever. They're very cheap. I could get 25 of them for just $5, but also it's a long shipping time. And while I have had experience with this SSD 1306 chip, yeah, it's URC. Well, I have had experience with the SSD 1306 like modules. I haven't had experience. I've only really worked with these breakout boards, and for this application, I wouldn't want to use one of those because, well, you know, that's just more PCBs I would have to worry about soldering on, and like clearance and stuff like that, and it would look kind of bad. Like, I would want to use just like the bare connector. I don't have any experience using the bare connector because there's some like supporting circuitry I have to provide for that. And like in general, especially for projects like this, which soldering kit do I use? You know, the best soldering kit is not having to do the soldering yourself, in my opinion. Yeah, I have... Well, at the moment I have a Weller soldering iron that I use for projects. I used to... So I moved and I didn't have the space to take it with me, but I used to have like a rework station that had a soldering iron and a air gun in one. And I do miss that air gun. I will probably need to do some soldering. It depends on, like, okay, so I'm planning on using these people for my, like, PCB construction, and they also do assembly, and I am perfectly willing to pay the extra price for getting the PCB assembly. So basically they have their library of parts. And for any parts that we have that are in their library, I can just get them to assemble it. And it'll be an extra cost, of course, but much nicer than having to solder it myself. Ideally, the only components I would need to solder myself are, like, easily, like, hand solderable ones. That said, I do have access to a soldering oven. It is the purpose of the soldering oven is for research projects, but it's not like it's, like, super monitored, so I could, like, slip this on in there if I needed to use it for a second, but I would prefer not to. Now, that said, I want to have as much soldering as possible done for me, and then the rest I can do by hand, or, like, worst case scenario with the soldering oven. Okay. So yeah, that being said, I'm probably not going to go with the LCDs just for this iteration of the project. Like I said, I want to have a finished product. I probably won't have one, like, by the end of the year, but at least, like, you know, early January, mid-January. Because I do want it to be a holiday present for Pancake. That said, I might do, like, a, you know, advanced version of it, do another, like, revision on the hardware. And that, I might, when I have more time and I'm not on this sort of time limit, I might, get some of these and play around with them. And see if maybe that's a good one. Pancake uses she, her pronouns. But no, she is lovely. Yeah, I mean, that being said, I'm looking at where we are today. I think we made some good progress. What I'm thinking I'm going to do for these, like, individual, like, each of these is one button. I think I'm just going to have an LED for now. It was never really meant to be a surprise. Listen, it's hard to it's hard to keep it as a surprise when she's a mod in my chat. But yeah, for now, I think I'm just going to use an LED for indication, which we can then... I'm thinking 25 buttons plus maybe, like, a slider for volume and a slider for, like, pitch bending. I figure she could have some fun having, like, the ability to pitch bend a sample as it's playing. Yeah, and I can implement all that on the resources we have on this microcontroller. I can and I will, Pancake. I am excited to see what this does to your streams. So yeah, I think it's 6 o'clock now. I think I'm gonna call it for tonight. I hope everyone enjoyed the stream. And let's see. Tomorrow I will be back with Morpheon, who has been taking a break from Twitch for quite a while. We're going to do a collaboration playing Ace Attorney, the first one. And then probably, like, later that day, or no, that starts at 5. Probably earlier, I'm going to be doing Sonic Heroes, which we've almost finished with. So yeah, be sure to catch that. Let's see. If you want updates on what I'm streaming at a given time, good places to check that out are my Mastodon, which is linked in my About page, and the Discord, which is also linked in the About page, or you can type !Discord in chat.
What happens when life breaks down?
Yeah? Hi?
God himself.
I truly wish I could just filter out the songs with lyrics, but oh well. But yeah, hope everyone has a good evening, and I